Did anybody actually go through and attempt it? Tried to. Good. That's going through. Okay. We'll see what happens with timing with today. I would bet we'll have time to double back through. It is a good question because it reviews everything. Okay? It puts it all together in one giant mess of a question. Okay? So we will potentially review this at the end. Remember, if you download the slides, it lists out roughly all the things that you have to answer. So the single question of just what's the percent yield, before you even get to that, you have to treat all of those other questions. Okay? And each and every single one of those other questions has some kind of secondary knowledge that you would have to remember and be able to apply behind it. Okay? So it is a hard question because of that. This kind of question is something that if you have to move into 151, you should fully expect to see show up at least once or twice kind of per exam. Okay? Yeah, per exam. Yep, that's exactly what I said. Okay? So a lot of this content is stuff that should be like second nature. You're spending 5 seconds at most on. Okay? So we'll talk about that depending on our time. So the last little bit of content we got to get through is empirical formulas. Okay? So we know what formulas are. Empirical formulas become important for a particular class of compound. Okay? So ultimately what the empirical formula is the fully reduced whole number ratio of the elements within a compound. Okay? So if we looked at the formula for sodium chloride, what would we write? Sodium is Na, chloride is Cl. So we just write NaCl. Right? What is the whole number ratio for those elements within that compound? It's 1 to 1. There's implied ones in those lower right-hand corners, right? Right. Okay. Couldn't I have also written 2 and 2? Okay. That maintains the balance of the formula. Okay. But we said that that's not correct. We have to show the whole number, okay, or the lowest whole number ratio. And that was when we were looking at ionic compounds, okay, or salts. So we said we always had to take that down to a 1. Or we always had to take that down to the lowest value. If we switch to magnesium chloride, well, magnesium is Mg, chloride is Cl. Okay, would that formula be correct? Why not? Okay, because the charges don't balance. Magnesium is a +2. Chloride is a -1. To fix that, what do we need? 2 chlorides. Okay? Couldn't I have also written 2 and 4? Doesn't that still balance the charge? Okay? But I want the lowest whole number. Okay? So when we asked you for the lowest whole number, we were really just saying do it. We were kind of indirectly telling you an empirical formula. Though not quite really, because for ionic compounds, we always reduce it down to the smallest whole number. And what you may notice or may have seen in some of the questions if you look to the textbook or maybe even in the practice exam, is that when we refer to the unit of magnesium chloride, okay, we might call it magnesium chloride formula units. And we don't call it a molecule. Why do we not call it a molecule? Is magnesium chloride a molecule? Or sodium chloride a molecule? Or even a compound? Even a compound becomes kind of a weird word to place on them. Because when we look at the solid for sodium chloride, let's see if I can pull this off. Okay, we get a small sodium and a large chloride, and then what happens? This repeats a whole bunch, right? Okay. So if I were to say, look at the solid of sodium chloride, well, there's sodium 3 and there's chloride 3. If I expand this out to look at a larger amount of salt, the number of sodium atoms and the number of chloride atoms are going to be a lot larger. And yet, when I refer to the compound of sodium chloride, I always refer to it as NaCl. Right? I'm always reporting it as the smallest whole number. Even though when I look at the compound, they're all linked next to each other. Okay? And they're all connected. The reason why I do that is because it's an ionic bond in between, which means I can't really refer to it as a molecule. That's where the word formula unit comes in. Because when we look at the larger structure of a salt, it's a massive repeating structure. They're all interlinked. So I can't refer to it as a molecule because I can't reach in and say this is a single molecule that is different from the rest. They're all connected to each other. I could reach in and pull this out, or I could reach in and pull this out, or this out. Okay? I'm breaking the atoms or breaking the bond between those connections when I pull them out. Okay? So there isn't a nice, neat unit. That's why we refer to our ionic compounds based off of formula units. What is the reduced formula within it? Kind of, sort of? Okay. In this class, we've just approximated, well, it's just a molecule. Okay. It kind of is and it kind of isn't. Okay. The reason why we want to bring it in now is that what happens if we look at a new type of compound? Okay. Before we were concerned about these ionic compounds. Well, what happens if I look at a molecular compound? Let's ignore benzene for the moment. Let's pick an easier one. Let's pick carbon dioxide. Okay, so there's carbon dioxide. If I now look at solid carbon dioxide, what happens? I'm just going to get a bunch of these carbon dioxides chilling around each other. When I reach in, I could pull out a carbon dioxide. Could I reach in and pull out, whoops, I wanted a different color. This is carbon dioxide. Green versus purple. Okay. Getting some heads being like violently, no, you can't do that. Purple shows carbon dioxide. It's showing the chemical bonds connecting those atoms to each other. The green one still has carbon and 2 oxygens. But are both those oxygens connected to that carbon? No. Okay? That's because I have a distinct molecule. Okay? The green one becomes an incorrect grabbing. There's no way I could grab the green molecule of carbon dioxide. Kind of, sort of? Right? And the reason for that is the bonds in carbon dioxide are not ionic. They're covalent. That changes the interaction of how the solid comes together. Okay? That's also then going to change how I reference the compound. And this is where empirical formulas come into play. Okay, so let's clean this all out, and let's move to the compound benzene. Okay, benzene looks something like this. Okay, which for those of you panicking and thinking, oh my God, I would never be able to draw that, you're not expected to draw it. Don't panic. You're also not expected to know that this was benzene. Okay. This is one representation of benzene. All right? So when we look at that representation, what would its chemical formula be? Okay. We have carbon, we have hydrogen. How many carbons are there? 6. How many hydrogens are there? 6. If we tried to do the same thing to this compound as we did to sodium chloride and say, well, it has to be the reduced ratio, we would say CH. Right? So when I reach in and grab a molecule of benzene, do I grab just 1 carbon and 1 hydrogen? No, I have to grab all 6 carbons and all 6 hydrogens in one pocket. Okay? Because they're connected through that covalent bond. So that changes the interpretation. Now I have a distinct compound. With that distinct compound, I have to make sure I identify every single atom within the compound. I can't reduce that information out. Kind of, sort of? Okay. Molecular compounds have the rough equivalent of ionic compounds. That's this empirical formula in red. empirical formula in red. Okay, we're at C1H1. In black, we would have the molecular formula. Okay. And as we just discussed, which one of those is more important when we think about benzene? The molecular, because that identifies all of the atoms that go into it. Okay? So why talk about the empirical? What's that?
The base of
Why do I care about the base of benzene? Why do I care about getting to that?
Do you want to alter it or change it?
It's an artifact of how we identified compounds. Okay? If I take a molecular compound and I want to know what's in it, okay, I could run it through a sequence of reactions to determine the amount of carbon present, the amount of hydrogen, the amount of oxygen, or the amount of nitrogen. Okay? We did talk about this really, really quickly a long time ago. I think it was Proust, okay, where we talked about the law of definite proportions, I think, vaguely. We said, how could they figure out that we had the exact same number of things present in it? Okay? And it comes from taking our compound and doing very particular reactions with it to identify the amounts of each of the elements present. Okay? The problem with doing that process is because we don't know what the identity of the compound is, when we take a reaction and we start reacting things out with it, I don't know how much I'm starting with. All I know is that when I do this reaction, okay, with some amount of sample, I get 6 carbons, or I identify that there's 12 carbons present and 12 hydrogens. Okay? Well, do I know that I burned only 1 molecule? Or was it 2 molecules? Or was it 3 or 4 or 5? Because I don't know what the compound is, I can't identify that. Kind of makes sense? Okay? So because I don't know that, what I would then assume is I'm going to go all the way down to the reduced ratio, and I know minimally that has to be true. Ideally, I would come up with a way to scaffold up to figure out what the molecular formula was. I would use other techniques to try and figure out that information. Kind of, sort of? Okay. One of the reasons why I don't feel this topic is as important anymore is that we've come up with better techniques since then to identify the compound outright at roughly the same cost. Right? So if we have a better technique to identify our compound, why are we going through and looking at this kind of archaic method? Right? The idea is to reinforce the meaning of those subscripts. Okay? What does that 1 mean? Okay? For those people at home, we can go through and circle it in purple. What does that 1 mean? There is 1 hydrogen. There is 1 hydrogen. We can actually get more information than that. Per 1 carbon. There is 1 hydrogen per 1 molecule or 1 formula or empirical formula unit. Okay? We have conversion factors that allow us to relate those things. Kinda? Okay? Does it have to mean a single molecule? No. What else could it mean? Okay. Molecule is which type of measurement? You might be like, that's kind of a weird statement to make. A molecule is a unit. It's a piece. Okay. What is that measurement? Okay. Are people units or pieces? Yeah? Okay. So if I go through 1, 2, 3, 4, there are 4 people in the front row. What was my measurement when I referenced people? We've referenced it before. What is that? What is that measurement called? Ends with a C. Okay, Mr. Chocula.
Count.
It's a counting. Okay, it's a counting measurement. Molecules are a counting measurement. I can count the number of molecules. Is there another counting measurement? Furry little animal with a weird nose. A mole. Apparently we're on the same wavelength today. Okay. 1 mole of hydrogen for every 1 mole of carbon. Okay. So I have a unit that is tied to those numbers. Okay. I have a meaning behind them. That information I can use to kind of run these experiments and say, okay, well, if I ran the experiment and I found out that I had 1 gram of hydrogen, how many grams of carbon would I expect to find in the compound if this was my empirical formula? Well, is that 1 gram in the formula? It's what?
1 mole.
It's 1 mole. I specifically said 1 gram. Why would I say 1 gram for hydrogen? Can you convert grams of hydrogen into something else? Yeah? What could you convert it to? Moles of hydrogen. How? Periodic table. How many moles of hydrogen would there be in 1 gram? Roughly 1 mole. How many grams of carbon would you need to account for that? 12.01 grams. Okay? So you can take this empirical formula and relate that back to the mass found within an individual sample. Kind of makes sense? Your empirical formula only shows you a counting, but you can convert that counting into grams using all of the techniques we've already used. Kind of make sense? Okay. So, this is how kind of, I hate to call it meaningless, but how meaningless I think this concept is for empirical and molecular compounds, that I put it together in a sequence of steps. So if you want to solve for the empirical formula, ta-da, there's your steps. Okay? This is as close to a formula as you're going to potentially get for this concept. So for the empirical, convert your units into moles for each element. So you could be given grams for each element in a compound. Okay? Because the formula only allows you to relate moles, you need to convert those grams into moles. How would you convert grams into moles? Using the periodic table. Once they're converted into moles, we have to make sure that we have the reduced ratio, because that's what the empirical formula is. So how would you reduce the ratio if I said C4H2? It's a horrible thing to do, but okay. You now know it's C2H1. How did you do that? What did you do to go from C4H2 to C2H1? How? What did you say? Times by half. Why did you pick a half? And you said divided by? You divide it by the smallest one. Divide all mole amounts by the smallest mole. What's the smallest mole in C4H2? 2. So what do? I divided everything by 2, which meant that C4, or 4 over 2 became 2, 2 over 2 became 1. Okay? You did that very well. What ends up happening, though, is that when we typically, I'm not going to erase it that slowly, is that if we were going to go through and do a calculation, what we might end up seeing is that we get C 0.006 and H 0.03. Right? You might look at it, but well, that makes no sense for a chemical formula. Why does that make no sense? You need whole numbers for a chemical formula. And because I literally just made this up, I could easily have screwed this up pretty royally. So don't quote me on it. What would our empirical formula become? Why aren't you so fast? With C4H2, you were all over that and jumped straight to C2H. Why can't you tell me the answer right away? Okay, the small decimal numbers, meaning, are these easy numbers to do in your head? Which is the smaller number, 0.03 or 0.006? So 0.006, 0.006. So C1H, was it 5? Oh. It's still horribly wrong as a compound. You did that way faster than I expected, so that's awesome. I guess I wasn't horribly bad with that. Okay. The empirical formula becomes C1H5. Okay. We have to do that calculation now because it wasn't obvious to us. Does that make sense? Is that a yes? Okay. So we just follow the rules to figure it out. Your empirical formula is the element times whatever the whole number is, element times the whole number. To get to the molecular formula, okay, you'll determine the molar mass for the empirical formula, and you'll compare that to the molar mass for the molecular formula. Okay? In that comparison, because the molecular formula is just multiples of the empirical formula, you're just trying to figure out what that multiple is. Once you know the multiple, you can change the subscripts. Okay? So when it says the number from 2, it's referencing step 2 right above. Kind of, sort of?
I have a question.
Yes.
What about balance aspect? Does that not matter?
Okay. So there's an interesting question. What about balance aspect? What do you mean by balance aspect? Because I think I know what you mean.
Well, like if you have magnesium and
Good.
chlorine.
Okay. When you look at magnesium chloride, okay, would we be using empirical and molecular formulas to figure out magnesium chloride?
Oh, it's because it's the covalent bond versus
The empirical and molecular formulas are largely centered on covalent compounds. Why would we not do them for this ionic compound? Magnesium chloride, is that a correct empirical formula? No, why not? The charges don't balance out. So when you come up with this, like, well, what about balancing? Do I have to worry about balancing? Well, when we're asking you to solve, we should be asking you to solve for something where you can't balance the charges because we don't know the charges for carbon and hydrogen because covalent bond. Right? Magnesium chloride, you should be able to balance the charges, which means having you go through and do a bunch of calculations for it is a bit silly because what would you be able to do? Just look at the charges and know that magnesium is a +2 and chloride is a -1. I know I need 2 chlorides. Okay? So you could short circuit pretty much all of those calculations by just jumping to that conclusion. Does that make sense? Okay. Does that mean all ionic compounds are off limits? As we'll see on the very next step, no, because I screwed up and asked the wrong compound. Okay? And then 2, what if I asked you the formula for iron oxide? Would you need to go through an empirical molecular formula to determine the formula for iron oxide? So what I'm asking is, what is X and what is Y? Would you be able to do this? As an ionic compound, would you be able to tell me what X and Y are? Okay, we hear a suggestion of yes. Okay, so if we got an idea on yes, what you're saying is you know the charges so that you can balance the charges, correct? Yes. What is the charge on oxygen? -2. Good. What is the charge on iron? Okay. So I heard 2 answers shouted out, okay, that were different, which should immediately cause problems, because if those 2 answers were potentially valid, how would we know which one was the charge? We wouldn't. +2 and +3 are both valid answers for iron. Okay. Are you responsible for knowing the charge on iron? No. If you don't know the charge on iron, can you determine the amount of iron that needs to be there to balance the oxygen? No. So iron oxide would be an ionic compound that you could be asked to do the empirical formula on because you don't know the charge. If you don't know the charge, you wouldn't be able to solve it, right, without doing an empirical formula calculation. Make sense? Okay. So, an unknown compound of radium oxide is found to contain 0.726 moles of radium and 12.3 grams of oxygen. Okay. Just in case you thought you were blind, it does say of oxygen atoms. What is the empirical formula? Okay. So let's start to write down some information we know. What information do we know? We're dealing with radium and oxide. We're being asked to solve for the empirical formula. I want to know what X and Y are. Make sense? Okay. What units should X and Y be in? Moles. So I know X is going to be moles of radium, and I know Y is going to be moles of oxygen. Okay? Before we freak out and do the math, let's take a minute to breathe and be like, do I need to do any math? Did Mike screw up the question royally?
Yes, you would need to.
Yes, I did. Why did I screw it up?
Oxygen is in grams, not moles.
No.
It gives you the mole of radium.
No. Why did Mike screw it up? How do you know it's balanced?
-2 and radium is
Oxygen's a -2, radium's a +2. How'd you know that?
periodic table.
When you look at the periodic table, oxygen is one you are required to know. Radium is in the second column. And what do we know about the second column? They're all +2, which means you theoretically don't have to do any math. Okay? Except, this is in lecture. We're admitting my failures. We're still going to do the work. Okay, so X needs to be in moles of radium. Okay, am I given moles of radium? Yeah, cool. So given information immediately tells me that I know I have 0.726 moles of radium. Okay? Because this is, oh my gosh, a test, and I'm stressed on time, since I know X right away, I'm going to look for the answer that says radium 0.726. And then I don't really care where the oxygen is, or I'm hoping there's only one answer that has that, because then whatever it says next to oxygen must be correct. Would that be a correct empirical formula? Why not? 0.726 is not a whole number. We still have to do a calculation. Don't just immediately start jamming things in, right? Make sense? Okay. But we've got a decent first step. What do we know about our moles of oxygen? Okay. We actually only know that I have 12.3 grams of oxygen. I would need to be able to convert it into moles of oxygen. Okay. How do I do that conversion? Okay. Grams, moles, oxygen. Where do I find that conversion factor? Periodic table, 1 mole, 0.0 grams. We okay with that? Okay. So we'd enter that into our calculator, 12.3 divided by 16. 0.768 moles of oxygen, which means my answer becomes radium 0.726, oxygen 0.768. Oh my gosh, that answer showed up. That must be the correct answer. Whole number again. How do we do it? Which number is smaller, 0.726 or 0.768? 726, so I divide both of them by 0.726, which can cause all sorts of mathematicians and some chemists to freak out. Okay, and we'll address that in a second. Okay, for the top one, I'd get 1. For the bottom one, I'd get... Yeah, wow, thank you. I knew that. 1.05. So my answer is then radium and oxygen 1.05. Whole number 1.05 is roughly 1. Which, interestingly enough, is actually what you guys said it was from the very beginning. Make sense? Okay. Why would a mathematician complain? So let's erase some. Actually, are we okay to erase? We're all good with that? Okay. No?
Not yet.
Probably don't need that, so I'm going to erase that. You good? Why would a mathematician complain about what I've got written there? Oh, actually, dang it, not that one. Why would, dang it, no, a mathematician wouldn't complain. I lied. Yep, okay. So maybe I'll screw it up later. So we can talk about that screw up later. Okay, but this would work for your show your work. Make sense? Okay. Okay. Could we switch it up? Okay. What if a sample was composed of 24.0 grams of carbon and 2 grams of hydrogen? Okay. Does this one become a harder question? What do you think? Okay. I see a shaking head no. I would argue it's not harder. It may be longer, but that's it. I now have to convert 2 numbers into moles as opposed to 1, but the same basic process is going to run. Okay. I would have 24 grams of carbon, 2 grams of hydrogen. Okay. Because I've done this enough times, I know my end goal is going into moles of carbon. That information is found on the periodic table. 24, 12, 6 moles of carbon. Yes, I saw it. 2 moles of carbon. Sorry. Right. When we go through and look at the yellow 1 grams hydrogen, moles carbon, 1. Yeah, 1.01. I'm just going to pretend that that equals 1. And I would get 2 moles of hydrogen, which is the smaller number. They're the same, so I can now divide by 2. I would get 1 mole of carbon, 1 mole of hydrogen, and my empirical formula becomes C1H1. Make sense? Okay, so we cranked through that a lot faster that time. Okay? Instead of addressing where our target was, we kind of held on to that in our head and saying that's where I wanted to get. Since I know I need moles, I immediately converted my stuff into moles. Okay? Interestingly enough, supporting what the tutoring center told you to do, always convert to moles. Once we have the moles, we can then divide by the smaller number, and we get our 1-to-1 ratio, C1H1. Yeah? Okay. You good? Okay. Here's what I want to do and go through and erase. This is the part where I intentionally screwed it up this time to make mathematicians cringe. Why would a mathematician cringe about that? (24 times 1/12 equals 2, right? Oh, divided by 2 equals 1. So 24 divided by 12 equals 1. Why would a mathematician cringe about that? Because it doesn't equal 1. Yeah. Okay. We created what is effectively a run-on sentence in mathematics. Okay. Officially, you should be doing that as a separate line because it's a separate calculation. Okay. Why would you run it together in one line? Because you're lazy and you don't want to write a second line. I understand your logic. It should be really officially a second line. Clearly, I understand your logic because I went through and did that. This should really be written out as a separate line. 2 moles of carbon. Whoops. Divided by the 2 equals our 1 mole of carbon. Yes? Okay. Mathematically, this now makes cleaner sense. We have 2 separate equations we can solve. We good? Okay. Could we make it more difficult? Let's see. Oh, dang. I didn't have that one there. Yeah, I don't have that one there. Does this look familiar? Question there. It might be on the practice exam. It's the same question. That's dumb. Why did I create a new slide? This says empirical to molecular formulas. With that given information, can I get to a molecular formula? If I could, what would the question be here? What is the molecular formula? Are you being asked what is the molecular formula? No, that's because I can't get to the molecular formula yet. I need more information. A small amount of that same sample was tested using a mass spectrometer. What a mass spectrometer does is determine the mass of a compound. That's literally what it does. That's its whole goal. Okay? So it is then found to have a molecular mass of 78 grams per mole. What is the compound's molecular formula? Okay, so what was the empirical formula? C1H1, and we know that because we just did it. Good. Empirical C1H1. So let's run an example molecular compound. Okay. Keyword here being example. In this key or this example, I'm going to say that example molecular formula is C2H2. Okay? What is the 78 grams per mole? The molecular mass. Where would we find the molecular mass for a compound? Periodic table. So if I know my molecular compound is C2H2, what would its molecular formula be? What's that? Multiply what by 2? Nope, 78 grams was the actual question. Here we've got an example. How would I figure out the molecular mass for C2H2? The mass of carbon times 2, right? So we've got 12. Why is my... Oh, because I'm writing with an eraser. 12 times 2 plus 1 times 2, and I would get a molar mass of 26, yeah? Could I find the empirical molar mass? Yeah, how would I do that? Well, there's 1 carbon, so 12, 1 hydrogen, 1, and my empirical mass is 13. What is the relationship between these two numbers? Okay, so depending on our focus on which direction we're going, we might reference this differently. Okay? Arguably, we should be going towards the molecular compound, not the molecular to the empirical. Why would we want to go towards the molecular? That's what the question is focusing on, going towards the molecular. So we use the molecular as an example to see the relationship. So to go from 13 to 26, what do I have to do? I can accept add 13. That is technically true. And unfortunately doesn't help us out mathematically. Doubled it. I times by 2. What happened to the molecular formula? It doubled as well. Right? Because there's whole number relationships here, if we go through and now look at our actual compound, we'll call this actual, what information do we know? Well, CXHY, I don't know the actual formula, right? But what do I know? I know the molar mass. What is the relationship between 13 and 78? Okay. So now we're trying to establish that relationship, right? Okay. Most people find it easier to do the multiple here, but we can't do the multiple in this case because we don't know what our multiple is. So 78 back to 13, what do I need to do? Divide by
13.
Divide by 13, because I know minimally that has to be present. How many times does 13 fit into 78? 6 times. So what did I do to go from 13 to 78? I multiplied by 6. What should I do to go from the empirical formula to the actual formula? Multiply by 6, and my actual formula becomes C6H6. Oh, benzene. Not very creative. I apologize. Okay, kind of makes sense? So the example in between is just to establish that relationship. That's it. So that we recognize the pattern between them. You don't need to do an example every single time. Okay? And arguably you shouldn't. Okay? What we're trying to see is the relationship between the empirical molar mass and the molecular molar mass. Because the empirical is the reduced ratio, it fits into the actual compound a whole number of times. Why does it have to be a whole number? X and Y must be whole numbers. How are you doing? Some people saying yeah. Okay, good. The crux of this is recognizing that X and Y are molecules or moles. You could have solved this as molecules. It's harder to go from grams to molecules. Why? To go grams to molecules, what do you have to do? You have to convert grams to moles and then moles to molecules. That would work. That's fine. Why would we not want to do that? Because we can do it with moles. So why do that extra step? Make sense? All right. So if we look at our rules again, determine the molar mass of the empirical formula, divide the molecular molar mass by the empirical molar mass to get us a whole number, and then you multiply the empirical whole numbers, our X and Y, by our number from 2. That whole number solve. Make sense? That is empirical and molecular formula. Congratulations, you are done with Unit 3. Okay. The rest of the sequence of slides are going to be kind of review, so I just want to talk about some things. Okay. What I do want you to think about, and maybe you've already thought about it, okay, what are new content? Yeah, I don't want you to write about it. Okay, what is the new content areas that you think you're responsible for in this unit? Okay, what areas are you still having troubles with? What areas do you feel super confident about? And then, do you have specific questions? I lied. You should actually think about writing some of this down. Okay, so spend a couple minutes. I'll ask if you need more time writing stuff down here in probably a couple minutes. Okay, but try and reflect back on what you think the new content is. Okay, where you are having troubles when you go through and solve. Where are you super confident with the material? And do you have specific questions? Like what things should you ask me to do in the next half an hour to go back to? So just write it down. This isn't a quiz to turn in. This is just you writing stuff down, getting some information down for you to think about so that we can work forwards from the rest of the class period. Okay? Arguably, dimensional analysis or the unit factor method isn't really new content, but it drives virtually everything we've done in this unit. Okay? So that's the biggest part of this. Figuring out a mole of objects, what it equals. 6.022 times 10 to the 23rd objects, okay, or items. Periodic table, grams equals 1 mole. That's new content. Okay? Balanced chemical equations. This is the stoichiometry concept. And I would argue, as much as complicated as our stoichiometry equations or solves become, really stoichiometry is just saying converting the moles of A into the moles of B. It's interpreting a chemical equation. That's it. Everything else that is typically tied to a conversion that involves stoichiometry are the other individual conversion factors. Okay? Molarity was a good call. Gases. You're responsible for the 1 mole equals 22.4 liters at STP. Please be very, very careful with that conversion. Okay? For this exam, you'll have to be extra careful of it. Okay? Because I ranted and railed about it a lot. Okay? When is 1 mole equal 22.4 liters? At STP. And, ouch. And it's a gas. Okay? That has to be true. Okay? If it is not a gas and at STP, it won't work. How could I easily write a question to make you think, oh, I'm going to use that, but not be allowed to use it? All I got to write is at STP with virtually any question. And you go, oh, I must be able to use this. At STP and a gas has to be both conditions true. Okay? When it comes to the final, you won't have to stress about that extra little piece. Pretty much if you're seeing a gas, you should be using mole to liters without worrying about STP. Okay? So you guys are all worrying about the STP, but then missing probably the most important part. It's got to be a gas. Okay? PV equals nRT plays a small minor role on this exam. You will see that in future classes if you got to worry about it. The limiting reactant or reagent as a concept is relatively simple. That's like sandwiches from cheese and bread. Okay? Where it becomes more complicated is when we involve all of the conversion factors above it, okay, which is allowed. Percent yield as a concept is, again, relatively straightforward and simple until we bring in all of the concepts above it. And then the last new one's empirical versus molecular formulas. Arguably, you guys already knew that. You just didn't quite understand how to manipulate those systems. Make sense? Conversion factors, where to find them. We already saw this. This is one way to think about where they're all found. Okay? Every time we've brought in a conversion factor, we've asked, where do we find it? Why are we putting it in the way we are? Every time you do a dimensional analysis question, you need to be asking yourself that. What is the intent behind using that conversion factor? Don't just start jamming stuff in because there's too many conversion factors to worry about. Okay? Another way to look at it, I would argue this slide is more important for the unit thing up at the top. Your unit is always composed of 2 pieces, a measurement and a substance. Okay? If the substance changes, you will have to convert the substance. If the measurement changes, you have to convert the measurement. You can't do them at the same time, though. Okay, so you have to break those into separate conversions if both change. Okay, which, again, we've addressed multiple times. Okay, you need to be able to find the conversion factors allowed for this. Okay, you will no longer have the text to reference. You will have to either be looking at the front of the exam or pulling it from your brain. And even pulling it from the brain could mean I know where to find it on the periodic table. Okay? Or I know where to find it in a balanced chemical equation. Okay? I would argue that's still the brain. Make sense? So the more you can recognize where to find that information, the less cognitive load you're going to be putting yourself under, and the more likely you'll go through and do better on the exam. Okay? So everything is dimensional analysis. Okay. I want to address briefly because there are formulas out there. Those formulas I have intentionally not talked about for the very reason that students often overuse them and don't recognize the exceptions to those formulas. Okay. The reason I'm addressing this now is that I am fairly certain in the Tuesday lab session they talked about a chemical formula or a formula that you could use to go through and solve for concentrations. Okay? That formula has massive flaws. Okay? Okay? I cannot stress that enough. Okay? And the issue behind it is it's a mix, both on your part of misusing it and on the faculty for not recognizing that you're going to screw it up. Okay? They tell you, here's the formula, here are the exceptions. You tend to have selective hearing, and what do you hear? Here's the formula. And you don't recognize the exceptions, and you end up overusing the formula. So just be aware of that. Everything we've talked about in this class has been very intentional through dimensional analysis to ignore all formulas. Okay, we do have some exceptions. Pivner was a formula. Okay? It's intentionally done to avoid those formulas because mistakes can be made easily with them. Focus on your dimensional analysis. It'll work for you. Okay? So we've got the limiting reactant question. I can go through and solve this if this is where you have questions. If you don't have questions here, I would rather focus on those. Okay? So as part of that little time reflecting, did you go like, I don't know how to answer this question from the practice exam? What's that? Do this one instead of the practice exam?
Oh, wait, no.
Okay, and if we want the practice exam, that's fine, but I need to know what questions. I can't just be like, oh, this was the question that was on the exam. Remember, memory, not there. I mean, we can slowly start piecing through this, and that may give people time to flip through and be like, oh, this was the question I had problems with. Should we start with that? Okay. So we've got all this information out here. Remember that I identified all these little individual pieces, okay, of steps to move through. I may not move through them in sequence, but I'm going to attempt to at least piece together how we could attack it. And arguably, I'm not going to go in sequence. Because what I would argue you should do first is what are you trying to solve for? We want the percent yield. Okay? So what you would need to remember is how do we calculate a percent yield? Right after I said don't memorize formulas. What's our formula for percent yield? That is our actual over our theoretical. Okay? Times 100%, and I almost always leave that off, but then remember to calculate it later. Okay? So I need to know the actual and I need to know the theoretical yield. So I could read through this question and see, am I given actuals and theoreticals? The other part of this is that it's asking for a percent yield, and a yield would usually be something that we produced. So we're probably looking at a chemical equation, a product within this. So it might be helpful to piece out of that textual information what is the chemical equation. Okay? Saying I'm starting with a sample of magnesium hydroxide. Okay? So I'm starting with it. It's a sample, so that would be a reactant. And more textual clues. Reacted with hydrochloric acid, so also a reactant. The end of the reaction recorded a dry mass of magnesium chloride, which means a product. Okay? In that list, I'm only given one product, which means when I'm looking at my percent yield, I'm going to be looking at the percent yield for magnesium chloride. Okay? Because I don't want to write out magnesium chloride all the time. I'll go through and write out the symbol, magnesium chloride. And argue at this stage, I could probably get away with just doing that. Okay? Because we're all chemists and we cringe when we look at that and say that is horribly wrong because magnesium has a +2 and chloride has a -1. It's not that much effort to go back and say MgCl2. Right? The units. Right? What units do I want to use for my magnesium chloride? So number one, because it's percent yield, the substance must be the same. Which means the units are going to be the same. What units do I want to use? Why do you want to use grams? It's given to you in grams. Okay, so if I picked a different unit, I'd have to do more conversions. So since it's given to me in grams, I'll go ahead and use grams. Okay. Is there a number associated with it right now? Yes. Yeah, it's the 60. Okay, is that 60 an actual or a theoretical? That is our actual, which means the 60 needs to go on top or in the numerator. Okay? So to solve this, what do I need to know? I would need to know the theoretical. What is the theoretical maximum that I could obtain?
50.6 grams plus 45.0 grams.
Okay? So there's an interesting idea. The maximum would be 50.6, and this is a really good suggestion, unfortunately wrong, plus, where'd it go? 45.0 grams to equal whatever that equals. 95? 95.6 grams. Okay, what are you doing to get that? Why are you adding them up? Why do you think you are allowed to do that? They react with each other.
There's only one product given, so you think that
Is there only one product? Okay. The way I would determine if there was only one product would be look at the chemical equation. So far I've only identified reactants and products, but I haven't actually written out the chemical equation. If I start writing out the chemical equation, I start with magnesium hydroxide plus hydrochloric acid, right? And we would say that would go to MgCl, because we already did the 2, we'll throw the 2 in there. Okay? If this was a combination reaction, hell yeah, that works. Why does that work? Combining is not the word we're looking for. It's another C word.
Combination.
There's lots of C words, aren't there, today? Okay, we're concerned about the environment. What might we do to protect the environment? We might conserve the environment. Why is this valid? The only time that addition is valid because of conservation of mass. And conservation of mass would allow me to do this addition if this was a combination. Is this a combination reaction? How do we know it's not a combination reaction? I'll accept 2 answers. I'll accept 3 answers. Hydrochloric acid with hydroxide is an acid and a base. This is a neutralization reaction, not a combination. What else would work? Could call it a double replacement, also not a combination. Is it balanced? No. Could I balance it as written? No. Why not? I'm missing the hydrogen, I'm missing the OH. Which means this equation actually needs to be properly written as HOH or H2O, depending on your preference. Okay? Can I now use law of conservation of mass? No. I would know sum total magnesium chloride and water together must equal that. But since I don't know the amount of water, I can't determine the amount of magnesium chloride. Which means your idea of adding those up, while I really like that idea, and that is really important for short answer A in your practice exam, you can't use it here. Okay? Okay, so we have a chemical equation. This would allow me to convert to make magnesium chloride, right? I could convert the HCl into magnesium chloride. I could convert the magnesium hydroxide into the magnesium chloride. So if I had moles, I could do those conversions. Okay? Add to that extra little layer here, that relationship. What would that relationship be? How much magnesium hydroxide do I need to make magnesium chloride? Why do I not know yet?
Because it's not balanced yet.
The equation isn't balanced, which steps even further back. Now we're digging into Unit 2. We have to dig even further back. Before we even attempt to balance the equation, what do we have to ensure? That the compounds we wrote are balanced. Magnesium hydroxide, yeah, that's magnesium and that's hydroxide, but magnesium is a +2, hydroxide is a -1. This needs to be OH2. Okay. when I go through and attempt to balance this, we need 2 HCl there, we need 2 HOH there. Now the equation is balanced, and now I can establish those mole relationships. Yes? All right. So again, what I'm trying to come up with is the theoretical yield. Okay? There's another word that we could use instead of theoretical that could be helpful. To determine that number, what do I have to do? C word. And not conserve. Convert. I have to do a conversion. Another C word. Calculate. Okay, I'm going to have to run a calculation to determine the theoretical yield. So sometimes you will hear the theoretical yield referenced as the calculated yield. Why does it have to be calculated? I have to convert my substances, my starting materials, into products. That's going to involve a calculation. Okay? So I'm trying to determine the theoretical grams of magnesium chloride, right? Okay. What am I starting with? Don't I have to do 2 things? Yes, I'm starting with 2 different species, which means 2 different limiting reactant calculations. So I would start with the grams of magnesium hydroxide. Why would I start with that one? It was the first one there. Okay. And I would also have to go through and do it for hydrochloric acid. For those of you that want to get all metacognitive on it, you might ask why you were specified grams of hydrochloric acid, because that is actually kind of interesting. Grams is actually a poor unit to use for a measurement. Okay. I made it nicer. Can I convert grams of magnesium hydroxide into grams of magnesium chloride? No. Why not? Or, well, sorry. Are they the same thing? No. I had to fix the question. They're not the same thing, so I will have to run a conversion. What do I want to convert? Okay. So there's a suggestion for grams to moles. I'm okay with that. Again, I would argue the substance is the most important thing. Okay. Why the substance? Because the measurement unit didn't change, at least on the surface. Okay. The problem with converting to the substance is what is the measurement unit for converting substances? Moles. Okay. So we'll run the top one going with our substance converter first. Magnesium hydroxide in the denominator, magnesium chloride in the numerator, and of course I didn't provide enough space, so we'll write moles sideways. Okay. That conversion factor is found in the chemical equation. In this case, it is 1 to 1. What? You say I can't do that? Yeah, I can. Okay. So this isn't a can't do it, it's do you like this conversion here? Some people don't like putting that conversion there because no units canceled. That doesn't make it incorrect. It's still a valid conversion. Okay? But it doesn't cancel units. So you might be freaking out and say, well, you should have gone into moles first, Mike. Okay? Well, grams of magnesium hydroxide into, what were you going to say? Moles of magnesium hydroxide. Okay? So I'm not even changing the order. I'm just saying, okay, now I'll listen to you. You know, sometimes selective hearing goes both ways. Okay? Where do I find that conversion factor? Periodic table 13 or 32, 34, 34 and 24. 58? Close enough. 58 grams is 1 mole. Here's my selective hearing. What your method was I want to get rid of grams. You just got rid of grams. My method, I got rid of 2 things. You got rid of 1 thing. Okay? Which one's better? Doesn't matter. Whichever one you see and you're more comfortable with. Both need to happen. We now be in moles of magnesium chloride. What do I want? Grams of magnesium chloride. grams MgCl2, moles MgCl2. Where do I find that? Periodic table, 30, 71, 71 and 24. 95? I got a tentative yeah, so we're going to run with that. 95 grams to 1 mole. Moles of magnesium chloride cancel. I can now calculate and get a potential calculated yield. Before I use that calculation, what am I also going to have to do? Bottom line. I also got to calculate with HCl. Okay? I'll reverse my bad hearing, selective hearing. There it was. We'll go directly into moles first. This one is 36 grams is 1 mole. Okay, we look at our units. The grams of HCl cancel. Okay, I now need to get rid of the moles of HCl and convert them into moles of magnesium chloride. What was that? 1, 2. Magnesium, or sorry, those cancel. Moles magnesium chloride, grams of magnesium chloride. What do we say, 95? 95, 1. Moles cancel. Punch it in the calculator and I get a number. This is, please reconnect. Please reconnect. This one is ballpark less than 95. This one is ballpark lesser than 95. You're not laughing at me. Give me a little bit of credit. I didn't see you doing that calculation in your head. Okay. I think that means our HCl's are limiting reactant. Can I get some numbers on that? Less than 95, just for the record. Oh, did I really screw that up that badly? Do it again. I want a confirmation. I think I trust 59. Sorry, Maddie. Did you leave off this too? All right, we'll talk about that later, make sure. I think 59 makes more sense. 36 times 2 is going to be 70-ish. 45 divided by 70-ish is half-ish. Times 95. Half of 95. 59. All right. So the 59 should be coming out. You might be making it simple. You got it? Okay. 59. We pick the smaller of the two numbers to be our limiting reagent, which is our 59. We can now take the 59, dump it into here, and we run our calculation. What do we get as a yield? A really high percentage. I couldn't possibly be getting over 100% yield, so I must have put in the wrong one. I'm going to do 60 divided by 82. Both those numbers show up on the exam. Which one's the correct one? The more than the 100% one. Okay. Are you allowed to get more than 100%? Yes. What does that mean?
That means that
You screwed up experimentally. Okay. That doesn't make the calculation invalid. That means the experimental result was bad. That's perfectly okay. Trust your method. Okay. We have to stop there. If you've got questions about that detail, you can talk to me after class.